So now we're actually going to start solving some problems. So I don't know how many of you actually brought this handout along. Don't worry about it if you didn't, because I'm going to just write the questions on the board. Okay, so actually I'm going to start, I'm not necessarily going to do these in order. I'm going to jump around a little bit. Okay, I'm going to jump around a little bit. So here's the first problem I'm going to do, and it's actually the last problem on the review packet. So it's problem number 7 on the review sheet, and here's what it says. Find the 4-3 entry of A inverse where A is the following matrix. 2, 0, negative 1, 3, 0, 1, 0, negative 1, 0, negative 2, 1, 1, and 3, 1, and 0, and 0. So let's see if we can solve that. It's the last problem on the first review session questions. I'm in the mood to start with this one. No good reason, really. Okay, so when you see a question like that, what maybe comes to mind?
Try the adjoint method and then just...
The adjoint method. Anything else come to mind? Determinants, of course, that's part of the adjoint method. Does anybody want to do it with Gauss, Jordan elimination?
No.
Okay, so some people do. See, the thing is this. I did not ask you for the entire A inverse matrix, right? So that actually is kind of significant, because if you do the Gauss-Jordan method, where you, remember that's where you take this matrix and you slap the identity matrix next to it and work your way down to the identity and lesson, you'll actually get the entire A inverse matrix on the far right hand side at the end of that calculation, which is actually more than what I'm even asking you for. I just want to know one of the entries here, the 4-3 entries specifically. So maybe we can actually do less work if we use the adjoint method. Okay, so let me just remind you again, I already wrote it down in one of those formulas, but I'll write it down one more time. The A inverse is 1 over the determinant of A times the adjoint of A. So what we need here really, well, we need to find the determinant of A. Maybe we should start with that. Okay, so my next question is, notice it's a 4x4. I didn't want you to use the arrow method. I'm making you do it a harder way. To find the determinant of capital A, what would you like me to do?
Cofactor expand the bottom row.
Okay, Brandon wants to cofactor expand row 4. Why did you pick that row?
More zeros?
Okay, there's quite a few zeros there, right? Okay.
I was at
It's-
the top of it because you want to eliminate the numbers that aren't zeros, right?
Well, but if you do the top, you're right, you'd love to have more zeros in what's left after you do the crossing off, but the thing is, you'll have more terms. So you'll have, if you do the first row, you'll have 3 actual cofactors that you have to find, whereas the bottom row, you'll only have 2. Admittedly, the 2 non-zero terms that you have will both have a lot of non-zero entries in them, but there's only 2 of them to do. So I actually would prefer to use the bottom row. Okay? So let's expand the bottom row. Expand row 4. You could have also chosen the first column, I believe. You would have had equally good. Or the third column. I mean, there's different choices. Okay. So let's do that. So here's what we need to do. If you remember the cofactor expansion method, which I hope everybody is sort of getting down pat by now, you take the entries from whichever row or column you chose and multiply by the corresponding cofactors from that row and column. So we have a 3 here, right? But I'm actually going to jump ahead and realize that that is a negative position in my matrix, so I'm going to put a negative in front of it before I even have a chance to forget about that. So are we with me on that? Because when you do this, the plus minus plus minus thing, you're in a minus position. So it's going to have a sign change. Okay? So it's negative with the 3 out in front times the determinant of the 3 by 3 submatrix that you get by crossing off. We're going to cross off the first column and the last row, and that just leaves us with this upper 3 by 3, right? So I'll just write that down. 0, negative 1, 3, and 1, 0, negative 1, and negative 2, 1, 1. Okay? And then we're going across the bottom row, so plus, this is now a plus entry, right? Plus, minus, plus 1 times the determinant of, this time I'm going to cross off this column and this row. And I'm going to take the other 9 numbers that are in that matrix, which I can't totally tell here. 2, negative 1, 3. And then 0, 0, negative 1. I always read rows. I don't do columns, just the rows. And then the last row is 0, 1, 1. Like that. Okay. How do you want to do this first determinant here? 3 by 3. May as well go for the arrow method. It's easy, right? So I have to, how do we do that? We recopy, move this plus sign over. We recopy the first 2 columns. Recopy the first 2 columns, and we go along these diagonals, right? So the first diagonal is a 0. And then negative 1, negative 1, negative 2, that's negative 2. And that stays negative, and then plus 3, which stays positive. And now I'm going to do minus the other diagonals. So minus 0, and minus negative 1. Does that look okay? You good on that? Okay, how about this one? What would you like to expand, V? Okay, if I expand the first column, I get, let's just do this in our head for a minute. I have 2 times this little 2 by 2 determinant, which is 0 minus negative 1, if I do my little 2 by 2 trick. 0 minus negative 1 is actually positive 1. So would you agree that the answer is 2?
Yeah.
Okay. Here's another way to do it, just for your information. If you switch the second and third row, do that in your head. Switch the second and third row. Do you agree it becomes upper triangular? As soon as it's upper triangular, the determinant is just the product of the diagonal, which would be 2 times 1 times 1, right? After you, I'm sorry, 2 times 1 times negative 1. After you switch those 2. So that would be negative 2. But what happens when you switched 2 rows? Sign changes, so it's really positive 2. This is the same answer that we get by cofactor expand. I'm just trying to show off. I totally agree that Hui's way is fine. You can just cofactor expand the first column. But, you know, it pays to know how the EROs affect the determinant. So anyway, this becomes plus 2, I believe you said. Be careful with your parentheses and stuff. Make sure everything's clear, that you don't get confused. So this is negative 3 times 2, which is negative 6. Add 2 to that, and we get an answer. We should get an answer of negative 4. Should get an answer of negative 4. Everybody okay with that? All right, now let's go back to the original question, because that's not the final question we're being asked. We're being asked for the 4-3 entry of A inverse, which is this matrix here. We've got the determinant, which is a factor of negative 4 on the bottom. But the 4-3 entry of A inverse really comes from knowing the 4-3 entry of the adjoint matrix. Remember, this is a matrix here, right? And the 4-3 entry of the adjoint matrix is the same thing as what?
Matrix of cofactors transpose.
Exactly. So the adjoint of A, I'll write it here again, is the matrix of cofactors transpose. So if I want the 4-3 entry of this matrix, it really means that I want the 3,4 cofactor. The 3,4 cofactor of this original matrix. C34 is the way we would write it. I want the 3,4 cofactor. Everybody agree with that? The 3,4 cofactor. So let's think about how do we get the cofactors again. Well, the 3,4 position is this one right here. To find that cofactor, all I do is I cross off that row and column, and now my matrix is getting really bad. And I take the remaining 9 numbers, and I have to take the, so C34, I have to take the determinant of the 3 by 3 submatrix that I have just obtained by crossing off the 4th column and the 3rd row. So it's going to be the determinant of 2, 0, -1, and 0, 1, 0, and is that 3, 1, 0? Is everybody following me, or are there too many lines on that matrix over there?
I actually think I just need a recap on
The matrix of cofactors?
it. Yeah.
Okay. Did you?
That's what I'm
Yeah, so that's the cofactors of 3, 4.
The 3,4 cofactor. Let's remember what the cofactors are. Actually, this is not quite the right answer yet. I need to do one more thing to fix it. But the 3,4 cofactor is what you get by basically finding the 3,4 minor and then putting a sign change into it, right? Because the 3,4 position is an odd position in the matrix. 3 plus 4 is odd. So the 3,4 cofactor is really, I'll just put it here actually, is the negative of the 3,4 minor. We would have written it this way. And the 3,4 minor is what? That's the determinant of the submatrix that you get after you cross off row 3 and column 4. So I crossed off, I probably should have done it in a different color or something. I crossed off the 3rd row and the 4th column, and I took only the other 9 numbers. This is no longer crossed out. Okay, I took these other, those 9 numbers, right? And I built a little 3 by 3 submatrix. So I take the determinant of that 3 by 3 submatrix, and then I'm going to change the sign because it's an odd position. So let's just calculate this determinant really quickly. This is negative of. All right, how do you want to do this determinant? So you're using what?
The cofactor.
Along what?
Huh? Column 3.
Right. Cofactor expand the 3rd column of this 3 by 3 matrix. You get a -1 here. Is there a sign change with that position? No. So it stays -1 times this 2 by 2 submatrix, which has a determinant of what? -3. So it's -1 times -3, which is +3, right? So this determinant is +3, but I switch to -3 because I've got the odd position in the matrix. So it's the minor is 3, but the cofactor is -3. Okay. So can somebody tell me, based on what we've done so far, what the final answer to this question is? 3/4. It's 3/4, right? You have a 4 on the bottom. Remember, the determinant of A was -4, so you have a -4 on the bottom of every single entry of your matrix. It's like factored out, right? It's a scalar out in front, and then you basically have to find the 4-3 entry of the adjoint, which is the same as the 3-4 cofactor. Right, Sergio? The transpose. Transpose switches the subscript. So if you take the transpose of a particular entry of a matrix, it literally switches the subscripts. And make sure everybody needs to know this basic information, right? That these subscripts are referring to row numbers and column numbers. So this is row I, column J. This is row J, column I, right? When you transpose the entry that is in row I, column J, the result ends up in row J, column I. They switch. Kind of what you're doing. So the 4-3 entry of A inverse requires us to find the 3-4 cofactor, which is what we did right here. Okay, so my final answer should just be 3/4. Everybody okay with what I'm doing so far here?
Is the matrix of cofactor the same thing as just the cofactors, or?
Yeah, the matrix, yeah, exactly. The matrix of cofactors is just literally the matrix that is made up of those cofactors, yeah. So I'll write it down here. So M sub C is literally just C11, C12, C13, C21, C22, C23, and so on. You'll find a good example of that in the lecture notes. When I was first talking about the adjoint, we started with the matrix of cofactors first. Then we just took a specific example. And you're just, remember guys, somebody's going to make this mistake on Wednesday. I know it's going to happen because I've taught this class 15 times. Don't let it be you. The mistake everybody wants to make is they take these cofactors and they multiply them by the entries from the original matrix. So you'll see people find the 1, 1 cofactor and multiply it by 2. I don't want you to do that. You only multiply the entries by the cofactors when you're expanding a row or a column to calculate the determinant. That's not what we're doing here. When we write down this matrix, we are not doing cofactor expansion. We are simply putting the cofactor numbers into the matrix. There's no expansion going on there. We are not picking any row or a column. We are not trying to find the determinant of the original matrix yet. We're simply making a new matrix whose numbers are the cofactors of the original matrix. But there's no multiplication by the entries from the original matrix. Yeah, Ed?
Okay, so just to make sure I'm getting it right,
Uh-huh.
for the, since right here is the negative determinant of that, right there, since,
Yeah. So I crossed off row 3 and column 4. So I've got basically these entries here, right?
yeah.
But not these.
Yeah. If, say that, you have the diamond around it, but if there was a 2 there, it doesn't affect, there's no 2 in front of here then, right?
Correct.
Okay.
Correct. The 3-4 cofactor. Yeah, that's a good point. It was kind of a bad example. Yeah, even if this was a different number, that number does not show up over there, right? Because I'm just writing down the cofactor. I'm not expanding a row or a column right now. Everybody understand the difference? It's a big issue. Somebody always makes that mistake, and I just don't want it to be you. Yeah.
If we did it the long way where we just like round the whole thing, would that be wrong?
For what? Oh, to do the A inverse? Oh, if you did the Gauss-Jordan method,
Oh no, just like,
or that whole adjoint,
yeah.
well, you're going to find 16 cofactors. You can do it if you want to, but I'm only asking you, really only asking you to find one. Right? This is my way of making a reasonable test question. If I ask you to find the inverse of this whole 4x4 matrix, I'm not sure that's reasonable for a in-class exam, a short amount of time, because you've got a lot of work to do, whichever way you choose to do it. Gaussian elimination or cofactors, adjoint method. They're both going to be very lengthy. So this is my way of testing you on whether you understand, the adjoint and the A inverse in terms of that, without making you do the whole thing. So I just say, find this one entry. I actually rather like that question. It took me quite a few times of teaching this class to realize I could ask that question and I would get what I want without making everybody do a huge amount of work. So I kind of like it. Okay, we all good with that? All right. As long as we're on the linear algebra, let me go backwards on the review sheet. Let's look at the previous problem, which is number 6. Okay. So number 6 says, this is actually number 2 for us, but on the review sheet it's problem number 6. So it says, write the solution set to the equation x1 minus 4x2 plus x3 minus 5x4 is equal to 0. Write the solution set. Okay? Write the solution set. So it's a linear system. Hold on a second. It's a linear system, right? Although there's only one equation in the system, so it's almost ultra trivialized. There's only one equation here, but it's a linear system. So the number of solutions is either 0, 1, or infinitely many, right? Those are always our three options. Which one is it going to be in this case? Infinitely many, right? Infinitely many. So, infinitely many means there are free variables, at least one free variable there, right? And in fact, the way we would normally deal with a problem like this is we would put down an augmented matrix. It's just that in this case, the augmented matrix only has one row, because there's only one equation. So it'd be 1, -4, 1, -5. Augment that with 0. Please be sure to put this bar there on your notation so that it's clear that that's what we have. And then what you would normally do is row reduce the matrix, but you see it's already in row echelon form. There's really not much else you can do. Okay? So what you'll notice here is that, remember, it always comes down to the pivots. And also remember that the entries of the matrix correspond to your unknowns on a column-wise basis. In a column-wise manner, the columns correspond to your unknowns. One of the morals of the story here, gang, and this is going to become more important as we move into chapters 4 and 5, is that what is important with these solutions to linear systems is where are the pivots, right? And which columns correspond to which variables. This is what's really important. A lot of people get hung up on other things they shouldn't be hung up on. A lot of people get hung up on, oh, I did EROs and got a row of zeros. Yeah, I'll hear people say that all the time. I got a row of zeros when I row reduce a matrix. And that actually is hard to really draw any conclusions from, unless the matrix happens to be a square size, which it generally isn't. So it's best not to get hung up on what's going on with the rows of the matrix. Focus more on the columns and the pivots. Okay? So when I see this, I have a leading variable, x1, and then I have 3 free variables, x2, x3, and x4. But the matrix is already row reduced. I'm not even asking you to do any EROs here. So what do we do next? Assign free variables to the unpivoted columns, right? So I'm going to come over here. I like to write my, by the way, this is another thing I'm going to recommend, that you write your variables down in the proper order from first to last. Some people, sometimes they start with the last one and they list them down this way, right? That gets, some people make a mistake then later because they don't write down the answer in the right order. So I like to list them in the proper order. So where do I start here? X4. Okay, what do you want x4 to equal? T. T, sounds good. It's free, right? It's not pivoted. Okay, what about x3? S, again, free variable, not pivoted. What about x2? R. R, very good. It's free, it's not pivoted. And then what about x1? X1 is not free. There's a pivot corresponding to it, right? And so therefore, we can solve for it in terms of the other variables. The way you normally would do it now is you would take this row of the matrix and rewrite the equation that it corresponds to. Of course, in this case, when you take this row of this matrix and you rewrite it as an equation, it just gives you that, right? Because this is actually a really simple problem. There's not much to it. So this is just going to amount to solving this equation for x1 and writing everything in terms of r, s, and t. So can everybody kind of mentally move everything to the other side with x1 solved for? What are you going to get? 4r minus s
Plus 5t.
plus 5t. Yeah, plus 5t. Okay? Now, is that the solution set?
No.
No. So when I ask you to write the solution set, what am I asking you to actually write down? The coordinate, the 4 components, right? So we write this in this fancy notation. Do you remember? The set notation. So we put x1, so we're going to make these parentheses here. And then we're going to put the first variable here, 4r minus s plus 5t, comma, r, comma, s, comma, t, close parentheses, such that, which is a colon, r, s, and t are elements of the real number set. Write it like that. That look good? Yeah, go ahead.
Have to leave it in the R's and G if you put in x1, x2, x3.
You know, that's a very good question, because you're sort of like, well, you just sort of renamed all these variables, but you could have just left it in terms of the original variables. You certainly could have done that. I would prefer that you do this, however, because this reminds you for sure that what you're doing right now is assigning free variables and solving for the leading variables in terms of those free variables. So I actually prefer this. I think it's not because this is more correct. It's just better for students who are just trying to learn this stuff if they kind of get in the habit of assigning these typical letters, so you remember this is the process you're doing. Yeah. So I recommend it, but it's certainly not necessary. Okay. While I'm on the subject of an example like that, I want to say one thing about another problem which I think came up in the homework, and I don't remember anybody coming to ask me about it. But if I had a matrix like this, that was something like this, 0, 1, 4 augmented with 3, and 0, 0, 1, 5, and 0, 0, 0, 0, or something like that, right? And that's my linear system, right, with that augmented matrix. Can you tell me if my variables are, again, x1, this time we only have 3 variables, x1, x2, and x3 in those columns. What can you tell me about x1?
There is no 0.
Right, if you actually go back with this matrix and you write down the equations that you would write down would be these equations, right? Right? And you see that there's no x1 ever mentioned. So what a lot of people make the mistake here is they assume that since this is a column of zeros next to this x1, they think that means x1 is equal to 0. But actually it's quite the opposite of that. When you get a column of zeros like that, it really means that whatever variable corresponds to that column doesn't show up in any of the equations. And a variable could never be freer than that. If the variable never shows up, you never see it, then it can be any number you want. The solution system to this equation, would be free variable for x1. I guess x3 has to be 5, and so x2 has to be negative 17. So it'd be something like that, except I've got to do my such that t is an element of R. Okay, so this isn't on the review sheet, but I remember it now because it came up in the homework. There was a matrix where you had a whole column of zeros here. Right? Everybody good with that? There is an unpivoted, I already put it in row echelon form. There's an unpivoted column. There's an unpivoted column there. That means there's a free variable corresponding to that unpivoted column. So in the world of 0 solutions, 1 solution, or infinitely many, this one has infinitely many, right? Is this matrix, is this 3 by 3 matrix here invertible, by the way? Couldn't be